Hi, welcome to Module 7 of Video Lecture 4. This is the penultimate module of this lecture, and here I'm going to present to you the last of the rules for calculating derivatives we're going to cover in this course. And that rule is the product rule. The product rule is used probably a little less often than the other two rules, but definitely less than the chain rule, maybe not so much less than the linear rule. And it deals with situations like this, in which you have the product of two functions. Now, note that this is not covered by the other two rules. This is not the product of a constant or the sum of two functions, so the linear rule has nothing for us here. Nor is it a composite function. It's not g of f of x, it's f times g. So how do we deal with this? Well, we deal with it by using the product rule. Now, the product rule ends up actually being pretty simple. Derivative of h is equal to the derivative of the first times the second plus the first times the derivative of the second. That's it. It's actually fairly easy to remember. If you do enough of this, you get really used to doing this. Basically, the thing you must remember is take a derivative of everything, multiply it by everything else that's not differentiated. So, first one times everything else plus the derivative of the second one times everything else. If you had three things, you would have three terms in this. We'll go through some examples like that eventually. So that's it. How do we get that? So again, I think it's kind of useful to go through and derive these things so you can see where they come from, that they're not mysterious. It's not some kind of random arbitrary thing. It all comes from the exact same definition of the derivative that we did in the previous lecture. So let's just do that. This one's a little more involved than the previous one, but not so much. Okay. Limit as h goes to 0 of f of x plus h times g of x plus h minus f of x times g of x over h. There's the definition of the derivative in this case. F times g, you plug in x plus h in the first term, you plug in x in the second term, you subtract, you divide by h, you take a limit. Same thing we've been doing. Let's now add and subtract to the top this term right here, f of x times g of x plus h. Since we're only adding and subtracting to the top, there's no problem here at all. So this becomes the limit. I'm going to drop the h goes to 0 part because it's understood. Of f of x plus h times g of x plus h minus f of x g of x plus h plus f of x g of x plus h minus f of x g of x, I ran out of room here, divided by h. Okay. So what do we got here? Well, we have a bunch of terms, but let's group them a little bit. These two terms have a common factor g of x plus h, and these two terms over here, I can't actually draw that on there, have a common factor f of x. So let's pull those out. Now remember, the product of the limit of the product is a product of the limits. So, first limit, we can pull out the common factor in the first one, and we get the limit of g of x plus h times the limit of f of x plus h minus f of x divided by h. All I do is pull out the common factor here. And then the next one, I'm sorry, this should be, yeah, that's right. And then plus the limit of the common factor, f of x, times, put it in parentheses, the limit of the rest of it, that's it. Now the first term, the limit of g of x plus h as h goes to 0 is just g of x. The second term over here is the definition of the derivative of f. This term over here is just f of x, there's no h in it at all. And this term here is the derivative, is a definition of the derivative of g. So we get as required g f prime plus f g prime, which, moving that around a little bit, is in fact the definition of the product rule. There you go. There's the product rule. Again, it may seem odd at first, but A, it comes directly from the definition of the derivative, like all the other rules we've done so far. And B, it's actually pretty easy to remember. If you just remember, you keep adding terms to a sum as long as there's one more thing to differentiate, right? So if there's two terms like this, you get f prime g plus g prime f. If there's three terms, you get f prime g h plus f g prime h plus f g h prime, and you can do that as many times as you want, right? So product rule is actually pretty convenient in that fashion. You just make sure everything is differentiated at least once. So that is it for the product rule. We'll do one example and then talk about the quotient rule. For example, we'll define a function that looks like this to make use of our new knowledge in exponentials. Now, you identify when to use a product rule by looking for products. So let's call f of x this first thing in front, and then g of x the exponential. Then the derivative of the whole thing is equal to f g prime, I flipped them to make a difference in the slightest, f prime g. So we need f prime, which is 2x plus 0. Right? There's a derivative of x squared is 2x. Derivative of a constant is 0. G prime is equal to e to the x again. So we can plug that in and get x squared plus 7 e to the x plus 2x e to the x. And we're done. That's the product rule, right? Not too complicated, right? Again, the chain rule requires some thinking about what to substitute where. The product rule is more of a brute force rule. You just go in, you take the derivative of every component, and you plug them into the product rule. Not much to that, conceptually. Now, people tend to have more trouble with what's called the quotient rule. The quotient rule, which you can memorize if you want, deals with situations like this, in which you have a ratio of two functions. There's a quotient, right? There's a ratio of two functions. The quotient rule is this. It's f prime times g minus fg prime over g squared. Now, you can memorize this if you want, and a lot of people do. Sometimes I use that for memory. But I find that just being presented with that is a little odd. It's like, well, where does that come from, right? We've given all these other rules that follow naturally from the definition of the derivative, and often have some kind of intuitiveness. This one seems to have a little less, in my opinion. So let's really quickly see how this works. Now, f over g of x is just a product. Let's define a function k of x equals 1 over g of x. I can do that. Well, then h of x is equal to f of x times k of x. Right? So far fair. Well, again, h prime by the product rule is f prime k plus fk prime. Right? So far so good, right? Nothing fancy. It's the product rule we just did a second ago. Gives you this directly. The only complication is k prime. We don't care about k, we care about g. So we have to represent k in terms of g. So k itself is easy. The first term here goes to f prime over g, just replacing k with 1 over g again. What about the second term? Well, what's the derivative of k? For this, we can use the chain rule, right? Effectively, k equals a function, let's say, L composed with g of x. G of x is just g of x, where L is equal to 1 over x, right? K of x is the function L of g of x, where L is 1 over x, right? 1 over g of x is the function, so you plug in g of x into the x here to get 1 over g of x. That's L of g of x. Okay, so if that's our function there, we can use the chain rule to figure this out. The derivative of k prime, I'm going to skip little steps here, is equal to the derivative of the outer one evaluated at u, in this case, derivative of this. So actually, you know what? I'm not going to skip steps. Better not to skip steps at this point. So to get that many different steps, we make u equal to g of x. We need the derivative of L at u. If you call the derivative from the power rule, x to the negative 1 equals 1 over x. So you pull down negative 1, subtract 1 from the power to get negative 2. This thing equals negative x to the negative 2, or negative 1 over x squared. G prime is going to stay by itself, because we don't know what that is. So we plug back in g of x into L to get L prime of g of x equals negative 1 over g squared. And multiply it back in with g prime of x to get k prime equals negative 1 over g squared times g prime. Plug that in over here, you get f g prime divided by negative k squared, sorry, chi squared. This thing equals f prime over g minus f g prime over g squared. Multiply top and bottom of the first one by g. Remember, this all works as long as g is not 0. And you get f prime g minus f g prime over g squared. That's the quotient rule. So you see, you can get the product rule, get the quotient rule directly from the product rule with an application of the chain rule. So the quotient rule is not anything different. It's not some odd, fancy thing that just appeared from nowhere. It's just the quotient. It's just the product rule applied to a function that's a composite of a function and 1 over x. That's it. If you want to memorize the quotient rule, you're more than welcome to do so. I'm not going to stop you. It's faster in a bunch of ways. If you want to treat everything to the product rule and just go through and differentiate and use the chain rule when you need to, you can do that too. Whatever makes you happy, whatever you find easier, you can do that. They both work the same way. And the textbook give a longer example, which we go through and do the derivative of a quotient, both using the product rule and using the quotient rule. In fact, I'll do a sort of simpler one here to close out this module. Okay, so we're going to use a relatively simple one. H of x here will equal 2x squared plus 7 divided by 5x minus 1. Okay. So a simpler one than we have in the book. So now we can use the quotient rule or the product rule. Let's start by using the quotient rule. So for the quotient rule, the f is on top, the g is on the bottom. We'll need the derivatives of each. So we'll have f equals 2x squared plus 7, and the derivative of f will be 4x. Right, again, we pull the 2 down, x squared, the derivative of that is 2x. 2x times 2 is 4x. G is the bottom in this case. 5x minus 1. Its derivative is just 5, because the derivative of x is 1. 1 times 5 is 5. Now I can apply the product, the quotient rule, which says that this is f prime g minus f g prime divided by g squared. All you need to do is plug in there. The hard part is remembering it. So we have 4x times 5x minus 1 minus 2x squared plus 7 times 5, all divided by 5x minus 1. So that's relatively straightforward. We're done already. We've calculated this derivative of this complicated quotient, this ratio, by using the quotient rule. If you can remember the quotient rule, that's probably fastest. If you can't remember it, don't fear. You can do this whole thing again using the product rule. Get the same answer as we'll go check right now. Same f as before, but now g is going to be 1 over 5x minus 1. What's g prime? Well, g prime is going to be, if we make g equal to, let's say, L of k of x, where L equals 1 over x and k equals 5x minus 1. So what's g prime? Well, we make u equal to 5x minus 1. G prime of u is equal to the derivative of 1 over u. Remember, that's just a power. So there's a power rule. Derivative of 1 over u is the same as the derivative of u to the negative 1. You pull down negative 1. You subtract 1 from the power to get negative 2. Therefore, this is 1 over, so negative u to negative 2, which equals negative 1 over u squared. Now, k prime here is just 5, which I said before. And, let's read k, sorry. K prime is just 5. We know g prime of k of x is going to be negative 1 over 5x minus 1 squared. And multiplied by k prime is 5, you get that g prime is equal to 5 over 5x minus 1 squared. Negative out front. Now the product rule in this case is equal to f prime g plus fg prime. That first term is equal to, let's see where the f prime was 4x. G is 1 over 5x minus 1. Then f is 2x squared plus 7. G prime is negative 5 divided by 5, so it's negative this, 5x minus 1 squared. If you take the negative out front, before the 5, and we multiply the left term over here, top and bottom, by 5x minus 1, we get the exact same thing we got in the quotient rule. It took a little more time, it's true, but it had the advantage of not having to remember any quotient rules. So which one you want to use, again, solely depends on what's better for you. If you're the kind of person who likes remembering quotient rules or additional rules, by all means, memorize the quotient rule and use it. If you don't like memorizing additional rules, you want to stick with a small number, the product rule works for all these cases. And that's it. You now have all the rules needed to do most derivatives you ever see in political science and social sciences in general. There are a few special cases we mentioned in the book. There's some trigonometric cases, but again, you can look those up. They don't come up very often at all. There's cases of piecewise functions. Piecewise functions are usually not differentiable at some points, the points where the different pieces connect, usually. But you can differentiate each individual piece separately using the rules we just did and get at least the derivatives in different areas. But by and large, you're pretty much done with all the rules you need. Again, we had 6 modules devoted to rules, 3 types of function, 3 types of rules, and one of the types of functions were the same as the exponential pretty much. So really much less than you might have thought originally goes into calculus. The derivative is a pretty straightforward thing. Even if this seems like it was kind of long, you'll find that it's just practice. If you work at this and you practice and you do examples, you'll find you get faster and faster at taking derivatives. You keep in mind only these rules, they go faster and faster, and before you know it, you'll be doing these derivatives that are complicated without too much effort. And to show you how this might work and how you should, in general, go about approaching derivatives that are more complicated than the examples we've given so far that you can just apply a rule to, the last module of this lecture, we'll go through and talk about a sort of a general approach to taking more complicated derivatives, and then give a couple of examples of more complicated derivatives that we'll work through together. And again, there are lots of problems in the problem sets and problem sessions. You can go over some work problems together, and more practice in this stuff is just incredibly important. Probably more important than practice in any other area of this course is the practice in calculus, because it's foreign to so many people that getting practice and working through examples over and over again is just incredibly helpful. So thank you very much, and I'll see you in the next module.